Good morning, everyone. Welcome to Concept Class. We've learned how gears give motion, sensors give awareness, and actuators make robots move. But today, we'll explore the most important part, the controller or the brain of a robot. It decides what to do, when to do it, and how much force to apply. A control system simply means something that controls how another system behaves. It takes inputs, checks the results, and adjusts until everything is just right. Think of it like your brain controlling your hand's motion when you write neatly. Control systems are all around us, in the fan regulator, in the fridge, and in the air conditioner. When the room gets too hot, the AC senses it and cools it automatically. That's feedback control in action. In a manual system, we make the adjustments ourselves, like turning the fan knob to increase or decrease speed. But in an automatic system, sensors and controllers handle it on their own, like a smart AC that adjusts cooling automatically. Now, let's discuss control systems in robotics. In robotics, the control system is what keeps everything coordinated. The controller receives data from sensors like position or pressure and then sends commands to actuators to move exactly as needed. This is the control loop. The input tells the controller what we want. The controller moves the robot through actuators. Sensors check if the goal is reached, and feedback goes back to the controller. It's just like your brain, muscles, and nerves working together. Every robot follows this same process. The input is the instruction. The controller makes decisions. Actuators act. Sensors check results. And feedback keeps refining the movement. Now, we'll discuss the controller, the brain of the robot. The controller is the robot's brain. It can be a microcontroller like Arduino or an industrial PLC. Both are designed to take decisions in milliseconds. The controller interprets the data, just like your brain interprets your senses. The controller acts continuously, it reads the environment, checks if the movement is correct, and adjusts in real time. That's what allows robots to work with human like precision. This control loop repeats many times per second. For instance, when a robotic arm is supposed to lift 10 centimeters, the controller keeps checking the sensor reading until the arm reaches exactly that height, not more, not less. Now let's talk about integrating sensors, actuators, and the controller. Integration means linking all parts together. Sensors tell what's happening, the controller decides what to do, and actuators carry it out. It's teamwork inside the robot. Let's see how this works in a robotic arm. The controller sends current to the motor to move the arm. The position sensor measures how far the arm has moved and sends data back. If the arm hasn't reached the target angle yet, the controller adjusts the motor instantly, ensuring perfect angular control. This is a perfect example of closed loop control. The robot doesn't just move, it knows how much to move and stops only when the target is achieved. This precision is why robots can assemble microchips or even perform surgery. Now, our next topic, manual versus automatic control in robotics. In manual control, humans decide every move. In automatic control, the robot decides for itself, using sensors and programmed logic. That makes it much faster and far more accurate. To sum up, sensors provide awareness, actuators provide movement, and the controller provides intelligence. Together, they create a robot that can see, think, and act almost like a human. So, next time you see a robot moving smoothly or picking up an object perfectly, remember, behind that precision lies an intelligent control system, constantly thinking, adjusting, and learning.